Alright, welcome to this particular video, which we're going to talk about diffusion. And we're going to talk about specialist diffusion when solutes are crossing a cell membrane, and we're going to discuss how that happens and what conditions are required for that to occur. Now, in previous videos we've looked at or reviewed the cell, and we know the organelles inside it, etc. We know that the cell is mostly water on the inside and it's surrounded by water on the outside. Now, in earlier lectures, when we talked about basic chemistry, we looked at the properties of water, and at that point we discussed that water was the universal solvent, meaning that you can put things into it, and because of the partial charge that it carries and the hydrogen bonds it's able to make between water molecules, that water can actually interact with other things that carry charge as well and cause them to dissolve. So when you dissolve something in water, you're referring to it chemically as the solute, which is dissolved in the solvent. So when I refer to the solute, I'm referring to whatever happens to be dissolved in the water. And in this case, there'll be things like sodium ions. So remember, we can put salt into water, sodium chloride into water, and stir it and it will disappear, which is dissolving. So sodium ions, potassium ions, calcium ions, magnesium ions, any type of ion will dissolve in water because all ions carry charge on them. Other things which are heavily charged, things like glucose, which are larger molecules, remember C6H12O6, fructose, are close relative to glucose, and then join them together and you've got sucrose. All of these things are well charged, therefore they'll all dissolve in water. So what does that mean in terms of diffusion? Well, I think in most of our lives we've come across many examples of diffusion and how things diffuse. For example, if there's a bad smell coming from your fridge, for example, then you may want to obviously remove the offending items, but if the smell is really quite potent, then you may get an air freshener and spray the fragrance in and around the area. After about 5 or 10 minutes, you may actually smell the same air freshener in another room. And the reason you're able to do this is because the particles carrying the fragrance, which were released when you squeeze the button on the air freshener can, have been carried through the air into the other room and are now actually binding in your nose onto the specialist receptor cells, stimulating the recognition of the smell. But how do they do that? Why do they get there? Why do they diffuse at all? Well, in essence, diffusion is really just the movement of solutes in a solvent in a liquid phase, or gaseous molecules in a gas, spreading out and reaching equilibrium. An easy test for yourself to do is to take any type of tea bag. Sun tea is a good example of this because a lot of people make it when it comes to summer. And you put the concentrated tea bag into a big container of water, and with the action of the sun to warm it up, you slowly see the brown liquid, which is just around the tea bag as it's put into the water, gradually spread across the whole of the container until after about an hour or so the liquid is uniformly brown. And this is a good example of a high concentrate at the tea bag, and the water just allows it to diffuse out over the entirety, and it continues to do that until it reaches what we say equilibrium, which is an equal concentration throughout all of the liquid. So why does this happen? And you haven't added any energy to this, you haven't added anything at all to make it happen, it's just happened spontaneously. Well, the reason why when you put, for example, sugar into water, it will dissolve and disappear, and then essentially after a while all of take a spoonful of the water out, it'll taste sweet, and every other one will taste just similarly sweet, is down to the molecules themselves and the atoms that make up those molecules, because all of them are slightly moving at all times. Now, that sounds a bit odd, but if you remember when we talked about the atom, we have the nucleus at the center and the electron around the outside. So if we just quickly remind ourselves of that, let's do helium. So it's not very well drawn. Let's do that one again. Let's just do 2N, 2P, it's just easier. So there's our nucleus of helium. Now it's got 2 protons, so it's going to have 2 electrons. It's going to have one here, say one here. Now if you recall, we were saying that the electrons orbit the nucleus. So that means that the electrons are actually moving. So in a molecule, which is all, and helium falls out at that point because it's a noble gas and doesn't form with other atoms. But for example, in sodium chloride, you've got sodium and you've got ions. You've got the sodium ion, you've got electrons on the sodium moving in one direction, and you've got the chloride with their electrons moving in all random motion. So, got this. Not brilliant, but if I spin that one that way, I can spin the other one that way. Well, these can be like electrons in and around a central nucleus. And if you join these on to many others, so you've got 20 of these all joined together, and they're all spinning in different angles, in different directions, then the whole molecule is going to jiggle. It's going to be moving around slightly. This inbuilt energy is referred to as Brownian motion, and all atoms have it, and therefore all molecules have it also. So everything in our universe is shaking, it's slightly jiggling at all times. And so if you hold 2 things together which are jiggling, they will bang off each other. And when they do, they'll move apart. And then they'll bang off something else. The closer you have all of these together, and they're all hitting each other, the further apart they will come from each other, until eventually they're just hitting each other every so often, and they're doing it at an equal rate. And that is essentially what equilibrium is. It's the spreading out of molecules in a liquid or gas, etc., which then allows them to only collide with each other every so often, the minimal amount of collisions. And so to do that, they have to spread equally across the area that they, or the volume that they are able to inhabit. So diffusion occurs by the action of Brownian motion, and Brownian motion comes from the motion within the atoms that make up the molecules. Now, to try and emphasize this, the only time you can make an atom stop jiggling is by taking it to absolute zero, which is a couple of 100 degrees below freezing. So that gives you some idea of how much you have to change the system in order to stop this natural phenomenon from occurring. So Brownian motion allows things to move. So when we draw in statics, say an oxygen molecule over here, well, that oxygen molecule is sitting there, but it's actually just moving. It's just jiggling about in this area. So it's there, and next time you take the picture, it's now there. The next time you take the picture, it's over here. It's just moving randomly around. And there's other oxygen molecules which are doing the same thing, and they will eventually bang into each other. When they do, that one will head that way, that one will head that way, and then they'll bang into another one and then send it off in a different direction. It's like playing a massive game of blind man's buff. You take a standard living room, take all the furniture out of it, take 10 people, blindfold all of them and get them to just walk around the room and just count how many times they bump into someone. The more people you add to the room, the more common it's going to happen. But of course people don't like to bang into strangers, so they try and just stay apart from them, and that's the whole point of the equilibrium. Alright, so if diffusion is the movement of a solute through a solvent until it's at equal concentration throughout the volume, liquid, then we can talk about that in terms of things moving across cell membranes. Now, diffusion itself is really just the movement through one, area with no barriers particularly in it. When you diffuse something across a membrane, then you can give it a slightly more specialized name. And if there's no energy input, it's still diffusion, then we call it passive or facilitated transport, because you're transporting from one side of the membrane to the other in the same way as, take the Mackinac Bridge for example, you can transport from the lower peninsula over the bridge to the upper peninsula and vice versa. So the membrane acts kind of like that bridge. So I've drawn on the board here passive transport, and I've drawn a bilayer cell membrane. Let's put transport in there. And I've put a list of things here that we covered in already and say that they can go in. So oxygen can go straight through, and that's only if it's in high concentration on this side. I'm shortening concentration to CONC and a little n at the top, to low concentration. And that's just the natural process taking place. If you've got very high concentration on one side, they're going to be colliding a lot. So they're going to be pushing further apart more quickly. On the other side, you've got very, very few. They'll only collide occasionally, so there's not much less pressure to go back across the membrane. Eventually, when it's equal, they will come across at the same rate, so they'll maintain that volume. So if oxygen's high outside, just put this in, so say outside the cell. And this is inside the cell. If oxygen's high on the outside, it will come through. CO2 high on the inside, building up, will go in this direction. Fats, steroids tend to come in, but they could also come out. Water can go both ways as well. Okay, so passive transport is the movement of things that can go through the cell membrane, the phospholipids, therefore they can get through the hydrophobic layer, and they just go from high concentration to low concentration. So passive means that the solute moves down a concentration gradient from high to low. So if we think about a hill, or say just take a slide, because kids like slides. So you take a soccer ball and you put it at the top, let it go, and it will run down quite easily to there. So that's going from high in height to low in height. But if you put the same soccer ball down here, it will not spontaneously go up to the top. So things will happen without an energy input that will go from high concentration to low concentration. So whenever we say moving from high to low, we're talking about passive transport. We're talking about diffusion, but passive transport if it's crossing a membrane, and even more specifically, if it requires help crossing that membrane, because remember, outside of this, things like sodium ions, put that one there, so potassium ions, glucose molecules, etc. are all, they're too charged, these are too big. And there's many other examples of this. So if that goes there, it will just get rejected. That will get rejected off there, that will get rejected off there. So the only way these things can move in and out of the cell is through these proteins. Now there's two different types I've drawn here. One is a channel. So the sodium, for example, if there's a sodium channel, could come in through there, if it's open. And alternatively, it could bind on here, sodium, and the glucose could bind there. Now I said in the last lecture, once they bind, because they're carrying charge, it causes the protein to change its shape. And it opens on the other side. That causes the, if you like, imagine they're sitting there and suddenly the seat just goes away, so they're just dumped off and they come out the only opening available to them, which is outside and back on the inside. So they need to bind. These are protein carriers, or you need to open up the channel and allow it to come through that way. So when you're using a protein, an integral protein, to cross the membrane, we refer to it as facilitated transport. You could also quite appropriately call it facilitated diffusion. These words are kind of interchangeable. Diffusion just means spreading out to reach equilibrium. Passive diffusion or passive transport is the passive movement of something across a phospholipid membrane. Facilitated diffusion or facilitated transport speaks specifically to the involvement of proteins to cross that membrane. So there's a more specific aspect to it. So remember, no energy input, diffusion, passive transport, facilitated transport. There is no energy input. It's from high concentration to low concentration. Thank you for listening.